Hi there. In this last part of the lesson, we will learn the second method of solving statically indeterminate structures that are under axially loaded axial loads. The last part we learned about the redundant force method. Using the superposition, we can analyze a member under axial loads by taking out one redundant reaction, and that would be a case under the external loads, and then analyze another case when we have the redundant support reaction put back, and we apply here the rule that the summations of the deformations should comply with the constraint of the original redundant reaction that we have in place. So the second method here is we will not change the member and split it into multiple cases like in the superposition and the redundant force method. We will analyze the member under its axial loads, and we'll use kinematics to study here the motion of one point or multiple points on the body of this member, considering the deformation information we have. So what is kinematics? Kinematics is the study of motion, knowing the geometry of a member, and kind of not considering the forces causing these. So we're more focused on the geometry of the motion. So if I say this member here, if I call this as a member, it's hinged on this side, and if I drop the end here by a delta or a deformation here, I know this delta is at the end of the member, so this means that the middle of the member will experience drop of half, right? Because now I'm using geometry to kind of imply deformation and displacements of a member here. So that's basically what kinematics is kind of mixing geometry and using the basic geometry information to relate between motions of different members in a system. So in this method, we'll use kinematics and our understanding of the system motion to relate the deformations that happen in the system. So if we revisit this same example again, and we'll analyze it as it is, we'll not take out a redundant reaction, we'll just analyze it as it is. So this is statically indeterminate. We have two reactions and one load here, P. And we'll start analyzing it considering we have using the unknown reactions here. So I still can draw here an axial force diagram. Not knowing the value of Fa and Fc doesn't prevent me from actually kind of drawing the internal axial loads in that member. So if I start from the top, Fa, the reaction here, I kind of predict that it will be pulling the member up. So that length of AB will be under tension, and the internal force here, FAB, will be equal to basically the reaction Fa. And once I hit point B, now point B is opposite to the direction of Fa, so this means that I'll add it now as a negative, and that negative value of P will make the chart flip, because now I know that this part BC will be under compression because the support at the bottom at C is holding the bar or the column from falling also. So it's kind of compressing the lower part of the column. And that compression internal force here is equal to FC. Sorry. So that's actually FBC should be equal to, if I take this out, so this one should be here equal to FC. All right. So now I have kind of a diagram as a function of the two unknowns I have, Fa and FC. So next would be to consider my boundary conditions here, or consider here that I have two fixed points or fixed supports here, A and C. So neither of them is moving. And I can also say that the movement of one relative to the other is also zero. So remember, the displacement should be relative to something. So a displacement of a point should be relative to another point. Now I have 2 points fixed, so I can say delta CA or delta AC is equal to 0. I can expand on that and say delta ABC. So I can now break this length AC to AB and BC and say that the accumulation of the deformation along the length of AB and along the length of BC will add up to the displacement of C relative to A, or from the boundary conditions or the support conditions here, it will be equal to 0. So knowing that delta is equal to PL over EA, now I can substitute each delta with the internal force and the length and the cross-sectional area and the material. The cross-sectional area and the material AE is the same for both lengths, so kind of they will be cancelled from my formula, and I end up with here the force and length of each segment here for AB and BC. So replacing now my lengths to figure out now that if knowing that now if AB, internal force of AB is FA, and FBC, the internal force here, is equal to FC but compression, so I put here as negative. Now I can have that equation that relates the two reactions FA and FC by knowing the deformation information and the kinematics of that member. It's simple kinematics, two fixed supports, so the movement of each one relative to the other is equal to 0. So, and now I can go to my always equilibrium equation to figure out the other relationship between my reactions. So this is the second equation in two unknowns, and I'll be able to solve for the two unknowns. And you can see here, it's the same values I got using the redundant force method. Kinematics method will give you the same answer. And kind of you can feel that they are almost, giving you or applying the same principles here. In superposition, I'm respecting that the deformation should equal to 0 at the support. Here I'm kind of using the same spirit to kind of put it in the context of kinematics. One thing to note here, that because P is closer to support C, then the reaction at C will be more than the reaction at at A. So FC will be 3/5 of P compared to FA 2/5 of P. So that will mark the end of this lesson. We learned how to calculate the axial deformation of a member, and we also kind of use this information to solve for statically indeterminate members using the two methods here, redundant force method and kinematics method. Thank you. I'll see you in other future lessons.